All right. Hey, everybody. Welcome back. So in this video and for this activity sheet, we are going to be looking at what I loosely call trig integrals. But more broadly, these are just integrals that involve trigonometric functions that can be solved using a combination of the techniques we've already discussed. So things like u substitution, for example, as well as some knowledge of trig identities. So things that you probably talked about way back in the day, back in pre-calculus, that have since sort of fled your mind. Things like the double angle formula, half angle formula, and what have you. So to get us started, maybe I should just say, scrolling through here, you'll notice there's just sort of a random assortment of these trig integrals that we'll learn how to compute. Like here we see cosine to the fourth of x times sine of x. If we scroll further down, we see something like cosine cubed of x times sine squared of x. And so we get a sense of what's out there, sine squared of x, and so on. And so in order to begin to approach these, we really want to remember some of our trig identities. And then as we're approaching them, we'll also want to keep in mind things like u sub or what have you. So what are some additional trig identities that will be useful for us in this sheet? Well, let's talk about these. I mentioned out loud the half angle and double angle formulas, and those are absolutely true. But full disclosure, I actually never really remember those. Or to be completely honest, I tend to struggle to memorize those. So the ones that I actually do remember are the Pythagorean identity. So I'll write that over here. Pythagorean identity. That's the one that says that for any given value x, if you take the sine of x squared plus the cosine of x squared, like this, that will always equal 1. Right? This was, this is the Pythagorean identity. It comes from the Pythagorean theorem or the Pythagorean formula. And specifically, it's simply pointing out that if you have a right triangle on the unit circle, let's pretend that's a nicely drawn triangle. If we have a triangle on the unit circle, here's an x value, and that's a right angle. It's on the unit circle, so this hypotenuse is 1. Then our two side lengths, right? The distance along the bottom, that is exactly the cosine function. So that's cosine of x. And what we have going up here, that's exactly sine of x. So the Pythagorean identity, this trig formula, really comes from the Pythagorean theorem, which was just a squared plus b squared equals c squared. So that's secretly what's going on here. Okay, so we've got the Pythagorean identity, and we've also got the sum formulas. At least I think they're called the sum formulas. And that's what happens if we have something of the form sine of a plus b, or similarly cosine of a plus b. And so these are the ones that I have memorized that I think are worth knowing. They come up time and again in various math classes. The sine of a plus b is just going to be, let me see, it's going to be sine times cosine. So that's sine of a cosine of b plus cosine times sine. So that's cosine of a times sine of b. So sine, cosine plus cosine sine. And then the other formula, the cosine of a plus b, that's just cosine cosine. So that's cos a cos b minus, right? So there's this sign change, sine times sine. So that's minus sine a sine b. All right, and so those are our three formulas, or at least the three formulas that I tend to refer to the most and the ones that I have memorized. Now, what does that mean for us as far as a double angle formula goes? I'm gonna slide over here. Hopefully the camera stays with me if we slide over. So we can use these formulas, these bottom two formulas specifically, to to calculate this double angle formula, let's say sine of 2a, and a similar cosine formula for cosine of 2a. And notice 2a is just a plus a. So we can really just use the sum formula from the left, except instead of a plus b, it's just a plus a. So sine of 2a, that becomes sine a cos a plus cos a sine a. So that simplifies down to 2 sine a cos a. While at the same time, if we go to the cosine formula, right, we get this double angle formula cosine of 2a, and that's just going to equal cos a, so that's cosine squared of a, minus sine a, so minus sine squared of a. And this is our double angle formula for cosine. Now for this one, I just want to mention, there are several different ways that you'll see this written, because notice we have a cosine squared and a sine squared over here, and those are exactly parts of the Pythagorean identity, right? We have a sine squared over here, we also have a cosine squared. So we can actually rewrite this piece in many different ways. For example, I could also write that cosine of 2a is equal to cosine squared of a minus, and then instead of sine squared, right, I could replace it with an equivalent expression coming from the Pythagorean identity. Specifically, notice sine squared plus cosine squared equals 1. That's equivalent to saying sine squared equals 1 minus cos squared, right? Maybe I should say sine squared of x equals 1 minus cos squared of x. So down here, instead of writing this minus sine squared of a, I can write minus, and I can replace the sine squared with a 1 minus cos squared. Right, and that simplifies down. That's going to end up becoming 2 cosine squared of a minus 1. Right, and so you have this equivalent formulation of the double angle formula for cosine, and you can similarly create one in terms of sine. So those are all formulas that will be helpful for us. And so let's take a look at how we might use these. I'm going to slide out of frame, or I'm going to move back over here to focus on this. I'm going to solve the first two problems. I guess that's problem 2 and problem 3, to point out how we can use these identities alongside U substitution or our other integration techniques. So for problem 2, let's see if we can zoom in here. For problem 2, if we're interested in solving this, we can do this in a more straightforward manner just by using substitution. So none of those trig identities will be necessary. Specifically, this is cosine of x raised to the 4th times sine. So we could just say let u, let's try that again. Let u equal cosine x. And then du, of course, will equal, let's think, not quite sine, but it'll be negative sine of x dx, because that's the derivative of cosine. And so this entire thing, with that as our choice of u, this becomes the integral of u to the 4th times, and then that negative sign, so this should end up becoming a du, but with an extra factor of -1, which I'll actually just pull out front right here. So that negative is coming from the negative sine of x, along with the fact that we're replacing a positive sine of x. So this is our integral, and then we can see this becomes negative u to the 5th over 5 plus c. And that just becomes negative cosine to the 5th of x over 5 plus c. And we're good to go. Now, that was just u substitution, but what happens if I have an expression like this, sine cubed of x dx? Right? If I'm trying to calculate the antiderivative of sine cubed, I might originally be stuck. There's not a clear cosine and sine that I can make my u and my du. So I might be in trouble here until I remember some of my trig identities. And specifically in this case, we're going to use the Pythagorean identity that we mentioned before. Again, we have this observation that we can replace sine squared of x with 1 minus cosine squared, right? That's our rewriting of the Pythagorean identity. And so this entire integral becomes the integral of, well, I'm going to siphon off 2 of my sines, right? So the sine cubed, I'm going to get a sine squared of x times sine of x. Right, so I'm splitting it up into those 2 pieces. And then the sine squared, I'm going to rewrite as 1 minus cosine squared. So I'm doing some clever trig identity and algebra manipulation here. So we get our sine squared became 1 minus cosine squared. The other sine just stays here as a sine. But now, let me scroll down just a tad. Now we can see that this is exactly, right? I can distribute the sign and rewrite this. This is just sine of x dx minus the integral of cosine squared of x dx. And so what we'll get here is the antiderivative of sine, which is, just negative cosine. And then minus, when it comes time to solve this problem on the right, we're going to use u substitution, just like we did above, right? Except this time, instead of a cosine to the 4th, it's just a cosine squared. And similarly, once the dust settles, we would end up getting that this is equal to, let me see, we still have that minus sign, and then this whole thing becomes an additional minus cosine to the cubed, or cosine, cubed over 3 plus c. So when all the dust settles, we're left with cosine cubed over 3 minus cosine, I should include my x's here, plus c. And that'll do it. So you see how we used substitution along with some of our trig identities in order to best actually compute this integral. And so we'll see many more examples of this throughout the rest of the sheet. Thanks so much, everybody. Have a great rest of your day. See you soon.